Hello, I'm SabahMusfiah and I'm from the Department of Electronics Convergence Engineering. Today I'll be presenting a summary of a research paper titled Advancements in Passive Wireless Sensing Systems in Monitoring Harsh Environment and Healthcare Applications. This study introduces the recent advancements in passive wireless sensor technologies, focusing on their increasing use in industrial monitoring and healthcare applications. These sensors work without batteries and provide wireless connectivity in a lightweight and miniaturized form, making them suitable for real-time and safe monitoring, even in complex or confined environments such as inside the human body or on wearable and devices. However, despite these developments, this paper points out that a comprehensive system framework for passive wireless sensors is still missing, which limits further optimization. To fill this gap, the review systematically analyzes application scenarios, system architecture, and key components such as the sensor module, communication module, and the readout module. It also presents case studies proving the feasibility of these systems in different sensing conditions. Overall, this paper lays a strong research foundation for developing advanced user-friendly passive wireless sensing systems. In this study, the authors discussed recent progress in smart sensing technologies, which has been driven by advances in materials, microelectronics, and data processing. Among these, passive wireless sensors have attracted significant attention because they can operate without batteries, are miniaturized, and offer wireless connectivity, making them ideal for real time monitoring in both harsh industrial and biomedical environments. While technologies such as surface acoustic wave sensors and self-powered sensors still face issues with stability, LC-based electromagnetic coupling sensors stand out due to their simple structure, flexibility, and broad detection range for parameters like pressure, temperature, and biomarkers. This paper focused on explaining the design and structure of both passive sensing modules and readout modules and examines their applications in extreme industrial settings and health monitoring systems. Ultimately, the goal is to guide the development of efficient and scenario based passive wireless sensing frameworks. So, this section explains the concept and development of passive wireless LC coupling sensing systems, which use magnetic coupling for wireless communication and battery free operation. This system solves the limitations of traditional wide sensing and can be customized for different application environments. The key is to design the system according to the sensing scenario to achieve the best performance. These are three main application areas: harsh environments, scenarios that can withstand high temperature, corrosion, and chemicals, often using ceramic substrates and stable electrodes to monitor temperature, humidity, gas, or pressure. Next is biomedical implants, miniaturized and biocompatible sensors used inside the body to measure biomarkers, pressure, and blood flow in real time. Wearable health devices, flexible and lightweight sensors for non-invasive monitoring of heart rate, motion, sweat, and tears without needing any battery. Each LC sensing system includes two parts: a passive sensor module and a readout unit. The sensor's resonant circuit made of an inductor and capacitor dictates environmental changes. These changes shift the resonant frequency, which can be observed as parameter variations on a vector network analyzer. So, to further improve performance, researchers have introduced several enhanced designs: intermediate relay systems, which extend wireless transmission by adding relay coils; vertically stacked sensors enabling compact multisensing through separate frequency bands; parallel sensing arrays allowing multiple parameters to be detected at the same time while reducing signal crosstalk. Overall, these LC-based passive systems offer high flexibility, scalability, and precision, making them highly suitable for industrial monitoring, biomedical implants, and wearable healthcare devices. This section focuses on the design principles of passive sensor modules used in LC-coupled wireless systems and how different structural types improve sensing performance for specific applications. The sensor modules are divided into three main types: signal stage structures, cascade, cascade structures, and specialized geometrical structures. The signal stage module is the simplest form. It includes a spiral inductor and sensing element placed where the electromagnetic field is strongest. Its sensitivity depends on the microstructure such as microarrays or cavities and on functional films like hydrogels or nanomaterials. These materials change the capacitance and resonance frequency when exposed to external factors such as temperature, pressure, and chemicals. Next, the cascade structures combine several sensing elements or technologies, for example, electrochemical electrodes or photoelectric arrays to detect multiple parameters simultaneously. They can be connected in layers or separated, forming interlayer capacitance that improve sensitivity. Finally, specialized geometrical structures like spiral stand-like or bracket-based designs are optimized for flexibility and stability. These are especially useful for implantable and wearable sensors where bending, stretching, or twisting changes the inductance and capacitance, allowing real-time monitoring. In summary, this design diversity enables customized sensor performance that can meet the unique needs of harsh environments, biomedical implants, and wearable healthcare systems within passive LC wireless sensing frameworks. This section explains the design and function of readout modules in LC-coupled wireless sensing systems, which play a vital role in accurate and efficient wireless data collection. Depending on the application, readout antennas are divided into three main types: loop coils, planar antennas, antenna integrated with processing circuits. First, the loop coils are the most common type. They can be single turn, multi turn, or coplanar and are typically made from metal wires. These coils generate localized magnetic fields that couple with passive sensors to collect data. Their geometry, wire diameter, and number of turns determine their inductance, resonance frequency, and sensitivity. Next, planar antennas such as microstrip or spiral designs provide a broader bandwidth and longer detection range compared to coil structures. Their performance depends on pattern parameters like the number of turns, line width, and spacing. Examples include coplanar waveguide fed monopoles, ultra-wideband antennas, and spiral planar antennas, all of which deliver high-gain multiband operation and excellent directional sensing capability, ideal for remote or wide area sensing applications. Finally, some readout modules integrate processing circuits such as oscillators, amplifiers, ADCs, and microcontrollers. This unit, these units enhance data precision, convert analog signals to digital form, and process or store the results for real-time monitoring. This integrated design ensures stable communication, high data integrity, and reliable operation even in complex or long-distance environments. Overall, the design of readout modules, whether simple coil-based or circuit integrated, is central to achieve accurate, efficient, and application-specific wireless sensing performance. So this section covers the main application of passive wireless LC sensing systems, which are mainly divided into harsh environment monitoring and biomedical monitoring, including both implantable and wearable devices. Starting with harsh environments, these sensors provide battery-free real-time monitoring of gases, temperatures, and humidity in high temperature, corrosive, or disaster-prone settings. And moving to biomedical monitoring, like implantable devices such as biodegradable LC coils, vascular stents, and polyimide copper spirals are used to monitor cranial pressure, blood flow, bladder pressure, or glucose levels through resonance frequency shifts. For wearable devices, flexible LC sensors attached to the skin, textiles, or contact lenses can monitor intraocular pressure, heartbeat, respiration, and motion. This typically use spiral or helical inductors combined with soft capacitive materials like PDMS or hydrogels. In biomechanics and motion analysis, sensor matrix embedded in insoles or joint patches map pressure distribution and gait patterns, assigning distinct resonant bands to each sensing cell. With the help of machine learning, these systems can localize movements and gestures accurately. In terms of body fluid monitoring, LC platforms can detect tears, saliva, sweat, or wound exudate using aptamers, hydrogels, or conductive polymers. Lastly, multiple signal systems such as smart garments, wheelchair mounted arrays, and electronic tattoos combine parameters like ECG, oxygen level, temperature, hydration, and pressure into battery free LC or NFC based networks for continuous health tracking. Overall, this application demonstrates how passive LC sensors are revolutionizing both industrial monitoring and biomedical systems, offering real time, wireless, and reliable performance. To conclude, passive wireless sensing systems offer an innovative solution for battery free wireless monitoring across industrial, environmental, and biomedical applications. This review summarizes the overall design framework, focusing on both the sensor modules such as single stage, cascade, and stent type structures, and the readout modules including loop coils, planar antennas, and circuit integrated designs. All of these components are interconnected through inductive coupling, enable reliable energy transfer and signal communication. However, despite significant progress, several changes still remain, particularly in accuracy, biocompatibility, and system adaptability. To overcome this, future research should explore AI based calibration, biodegradable materials, and integrated sensing therapy systems that can make these technologies even more precise, safe, and intelligent. Overall, passive wireless LC sensing systems are paving the way for next generation smart monitoring technologies, driving major advancements in healthcare, environmental sensing, and harsh condition applications. That's it for today. Thank you.